Hello. Today's lesson is part of the Kinetics, Equilibrium, and Thermodynamics unit. Our focus today is going to be chemical equilibrium. Before we get started, please pause and answer the question, what does chemical equilibrium mean to you? As we journey throughout the rest of today's lesson, you're going to be comparing what you think chemical equilibrium is to what it actually is. Hopefully, they're the same. If not, you have to unlearn what you think it is and learn what it actually is. So to start our journey of learning, we are going to watch an equilibrium demonstration. Sadly, the video doesn't translate into this presentation, so you're going to have to pause this recording and go into our Google Classroom to open up the equilibrium demonstration file that's in there. I do apologize for the instructor's head being chopped off. That's not what you need to look at though. The idea is what's going on the counter. When you're done watching the video, please resume this particular lecture. Well, that was fun. So, chemical equilibrium. After you heard that question first posed, did you think equilibrium meant equal amounts? That chemical equilibrium was established when you had equal quantities of reactants and products? If you did, you're not alone. If you did, you've got to unlearn that because that's not what chemical equilibrium really means. Chemical equilibrium is defined as the rate of the forward and reverse reactions are the same. That could be rephrased by saying the same amount of products are being produced as reactants are being reformed. Or perhaps you like to think of it as the concentrations of the reactants and products remain the same. As you saw in the demonstration, yes, sometimes you do have equal amounts, but more often than not, chemical reactions are not favored evenly in the forward and the reverse reactions. So how is it that we're really going to know, though? That was the ending question in our demonstration. Enter the equilibrium constant. The equilibrium constant is a ratio used to determine the expected outcome of concentrations when equilibrium is reached. Its symbol is a capital K. Since it's a ratio, there's some math involved. So how is it that this equilibrium constant is derived? Well, let's take a generic chemical reaction. We have reactants A and B producing products C and D, and the lowercase letters are simply meant to be the coefficients that would come in front of those formulas in the chemical reactions. What we've learned in our lesson is that when we're at equilibrium, the forward reaction, meaning the production of C and D, and the reverse reaction, the reforming of A and B, that's what's the same. So their concentrations at equilibrium will be unchanged. When I say equal, it's not, they're not always the same number, but their numbers are no longer changing is what we're really trying to hit upon here. So what we're able to do is derive this expression. And this is the formula for calculating your equilibrium constant. We are taking the concentration of our products Notice that they are raised to the power of their coefficient in the balanced chemical reaction, and we're going to divide that by the concentration of the reactants raised to their power of the coefficient. The denominator is the concentration of the reactants. And a friendly reminder that when you see those brackets, right, brackets always means concentration in molarity. It is important to note that if you have a chemical reaction where one of your species is either a pure solid or a pure liquid, they are not going to be included in the equilibrium constant expression. Only gases and aqueous states will. Only gases and aqueous are included. And perhaps you would like to think of that as, remember what we're trying to do is figure out how many particles there are. So in a pure solid and pure liquid, the molarity, which would be number of particles per unit volume or amount of space that you're taking up, that there's not going to be any difference, right? In a solid, your particles are so close together that the number of particles is the space that they're taking up. And for the most part, the same is true with your liquids, despite the fact that there's some space between the particles, allowing them to move and be fluid. But when you're talking about gases and aqueous states, solutions, the vast majority of our gases is empty space, so we definitely need to know how many particles there are per unit volume. And same thing with our aqueous states. Remember, the water is not usually part of the chemical reaction. The water is needed to take your ionic solid or your strong acid or your strong base and dissociate those particles so that they are existing in free-flowing ion form. All right, so before we get to the math, let's talk about what the math is going to tell us. So when we calculate these ratios, ultimately it's going to be letting us know where we're at with regards to equilibrium. So thinking back to our demonstration of the water levels in the buckets, there were three possible scenarios with regards to what the water levels meant. So in this slide, if when we do the math, our equilibrium constant comes out to equal 1, that means the concentrations of the reactants are equal to the concentration of the products. In other words, the buckets filled with water, they're literally going to be at the same height. So this is one where every number is going to be the same. This is what many of you thought chemical equilibrium meant, where we have equal amounts of reactants and products. In other words, the arrows in between these would wind up being identical. Neither is dominating. That's what's meant when you do the math and your equilibrium constant equals 1. If, when you do the math, your equilibrium constant is a number bigger than 1, that means, thinking of the ratio, the only way that this fraction can come out to be a number bigger than 1 is if the number in the numerator is larger than the number in the denominator. The number in the numerator is indicative of our products. So our amount of products are going to be greater than the amount of reactants, and the forward reaction is favored. So going back to our little buckets again for a second, and our demonstration, right? We had reactants on the left, products on the right. Here, our water levels are not going to be the same. Here we have more water on the product side, less water on the reactant side. More reactants are being used up to make products than the products are being used up to form reactants. So in this instance, when your equilibrium constant is greater than 1, the forward reaction is favored. And the third scenario is the one that was demonstrated in our video. If after we do the math, the equilibrium constant is less than 1, again, coming back to the math, the only way this fraction could be less than 1, a fraction, is if the denominator's number is larger than the numerator's number, and the denominator is information about the reactants. So when our quotient is less than 1, the reactants are going to dominate, which means the reverse reaction is favored. What does that look like with our buckets? The water level in the reactants bucket is higher than that of the products bucket, so our forward reaction is not favored, but our reverse reaction is. So let's get into some example problems where we practice the math. The first practice problem we'll do is the formation of ammonia. Nitrogen gas and hydrogen gas produce 2 molecules of nitrogen trihydride, which is commonly called ammonia. The question asks, what is the equilibrium constant for the production of ammonia if the concentrations at equilibrium are as follows? The concentration of nitrogen is 0.02 molar, the concentration of hydrogen is 0.02 molar, and the concentration of ammonia is 0.01 molar. What does this mean? Well, looking at my key concepts and the data that I'm given concentration values, and more importantly, those concentration values are at equilibrium. When you see that they're at equilibrium, that means you can now substitute in to your K expression. You cannot substitute into K if you're at any other state or any other time in the chemical reaction. The only data you can substitute into the equilibrium constant are the concentrations at equilibrium. So according to our generic formula, I need to take the concentration of my products, which in this case would be NH3, and I'm going to raise it to the power of its coefficient, and I'm going to divide that by the concentration of my reactants raised to their power. Double checking, I can only include gaseous and aqueous states, which all 3 of the species in my chemical reaction meet. They are all gases. So now I can start to substitute the numbers in. The concentration of NH3 at equilibrium is 0.0100 molar, and I'm going to square that. The concentration of nitrogen is 0.0200 molar, and the concentration of hydrogen is 0.0200 molar, but I'm going to cube that. Doing my math. Definitely double check my math. According to my math, the equilibrium constant value comes out to be 6,250. Notice that there's no unit associated with it. This is just meant to be a ratio. You will never find a unit associated with your equilibrium constant. And I'm not officially done with the problem because I need to ask, what does this mean? And I'm going back to that last slide that we just looked at. What does the equilibrium constant mean? So I'm either equal to 1, greater than 1, or less than 1. The number 6,250 is greater than 1, That means the forward reaction is favored. The forward reaction is favored. If I did my math wrong, please forgive me. Perhaps our conclusion will be different. So if my math is wrong and it winds up a number smaller than 1, then I'd have to say the reverse reaction is favored. If my math is wrong and it's really supposed to be equal to 1, then we would say the forward and reverse reactions are both favored equally. All right, let's look at a second example problem. Our classic example for our equilibrium and kinetics lectures, the formation of hydrogen monoiodide. So I'm given the reaction. I can see that all my species are gases, so I know they're all going to be involved in the equilibrium constant expression. I'm told what the equilibrium constant value is. Initially, the concentrations of hydrogen and iodine equal 1 molar. Calculate the concentrations of all 3 species at equilibrium. So I need to sort of work backwards. Now, what we learned last problem is that when I'm substituting into the K expression, they have to be the values at equilibrium. And when I look at the data that I've been given, I'm told that that's what it is initially. So these values of 1 molar can't go into the expression directly because they are initial concentrations, not the concentrations once equilibrium has been established. So we need to learn one more piece of new information with regard to the equilibrium constant before we can solve this problem. We need to learn about ICE charts. ICE is all capitalized because it stands for I, initial, C, change, and E, equilibrium. Initial is how the demonstration started. One bucket was filled with water, another bucket was empty. Then the chemical reaction began, and the levels of water in the bucket began to change. So we have to ask ourselves, does the amount go up or down? And it's important to know that the amount's going to go up or down based upon the mole ratio in the chemical reaction. And then finally, equilibrium is established. And these are going to be the values after this change has been applied. Let's go back to problem number 2 and implement this. I'm going to rewrite my chemical reaction, and I'm going to add some symbols to it. I'm now going to put my brackets in. I need the concentration of hydrogen plus the concentration of iodine. It's going in equilibrium with 2 moles of HI. And what I'm going to add down the side here is the ICE chart. The I stands for initial. The problem tells me that initially the concentration of hydrogen and iodine are equal, and they're both 1 molar values. So I'm going to fill that in. This is sort of like a table. Adding the grid lines to the table is too much for my eyes. If that's something you would like to add, you are welcome to do so. Oh man, the concentration of HI initially is not given to us. Think back to the demonstration with the water levels in the bucket. Did we have any products made before the reaction even started? No. That means that there's nothing. There are no products initially, so therefore the concentration is 0. All right. Next up, I need to figure out the change. The first thing that our notes said to do was figure out, does the amount go up or down? Well, I've got a chemical reaction here. I've got a certain concentration of reactants and absolutely no products made. That's an indication that the amount of my reactants are going to go down. They're going to be used up to make products. So the concentration of my products will go up. I now need to figure out, well, by how much? Since I'm not told what any of the equilibrium values are, I'm going to need to use a variable. I'll use the variable x. The notes that we took said that the change must increase or decrease by the mole ratio. Looking at my species, the hydrogen and iodine are in a 1-to-1 mole ratio, so their change is both going to be down by the same amount. I'm going to call it x because I don't know what the value is. The mole ratio produces 2 moles of hydrogen monoiodide on the product side, so I will have twice as much change on my product side. And therefore, at equilibrium, I'm going to wind up having 1 minus x for the concentration of hydrogen, as well as the concentration of iodine, and I'm going to have 2x as the concentration for my hydrogen monoiodide. I've simply done the math, the addition of initial plus change equals equilibrium. Now that I have these values at equilibrium, even though there's a variable, now I'm able to substitute in to the equilibrium constant expression. I can now say that K will be equal to the concentration of HI, and I'm going to square that, divided by the concentration of hydrogen times the concentration of iodine. Those don't get raised to a power because their coefficient values are 1. The concentration of HI is 2x. That will be squared. The concentration of hydrogen at equilibrium is 1 minus x. And the concentration of nitrogen at equilibrium is 1 minus x. Oh, cool. I was also told in the problem that the K is equal to 45.9. That's also going to help me know what way my change is. Since it's a number greater than 1, I know the forward reaction is going to be favored. Therefore, my products will go up and my reactants will go down. So cleaning this up a little bit, we've got 45.9 equals 2x squared divided by 1 minus x squared. Since my numerator and denominator are both squared, I can undo them by taking the square root of both sides of my equation. 6.77 equals 2x divided by 1 minus x. Starting to solve, let's get that 1 minus x out of the denominator. So I'm going to multiply both sides by it. So I've got 2x equals, now I'm going to factor this out, 6.77 minus 6.77x. Oh, sorry, I'm a little offline here. Going back to my algebra, I want to get the x terms to be on the same side of the equal sign. (8.77x). To solve for x, we would now divide both sides by 8.77. So 0.772 is what X winds up being. I'm not done yet. I need to go back in and redo this math. So 1 minus 0.772 equals 0.228. So the concentration of your hydrogen is 0.228 molar. 1 minus 0.772 equals 0.228 molar. That's also the concentration of your iodide. And then to figure out the concentration of your hydrogen monoiodide, we've got 0.772 times 2, which equals 1.54 molar. And that is as complicated as equilibrium constant expressions can be. At this point in time, please turn your attention to the practice problems provided in the Google Classroom, and let me know if you get stuck.